Alright, hi everyone, welcome to my YouTube channel CCF Electrons, and in this video we talk about starting torque, and we'll be kind of fast with it. Now, note that this is from the previous video, okay, literally from the previous video. However, all the videos in this series are one, so we just go through all the videos in this playlist are one, so just go through them. Now, when we say starting torque, is the torque developed by the motor at the instance of starting. So when the motor starts, like we start up the motor at that instance of starting, the torque developed by the motor, that is known as the starting torque. Okay, so at standstill, the flux is proportional to the EMF. Rotor flux proportional to the EMF flux. Look at this. Okay. Look at this, what we have here. Remember we said this, that the flux equals the angle between the rotor. The angle between the rotor and then the rotor EMF and the rotor current. Remember we said that in the previous video. Okay, so just bear that in mind, we'll talk about it. Now, look at this. Since we just said that at standstill the rotor flux is equal to the rotor EMF, that means at starting, our starting torque will be this. Recall that we said in the previous video that torque T equals what? This equals this, and then we have what? The flux here, and then cos, that's the power factor, and then this. This is what we said in the previous video, and we got this from the DC motor, from the idea of DC motor, but we said that in induction motor the power factor is considered. So we said this in the previous video. Now what we are saying is that at standstill, which means the rotor is stationary, it's not rotating, that means the motor is not working at that moment. So at standstill, this flux, the flux is the same or is proportional to the EMF. So meaning that this thing we have here, we can replace our flux with what? EMF. Are we seeing what's going on here now? We can replace it because they are proportional. This is at standstill, that means our starting torque can be written as this. Instead of writing our torque as this, which we'll do at standstill, which means the starting torque, we'll now say the EMF proportional to the starting, flux. So we can just replace it. Okay. Now, but remember from Ohm's law, recall that V equals IR from Ohm's law. Okay, and we can say from that, we can say I equals V over R. Okay, now in this induction motor, when we say resistance here, induction motor, we are talking about impedance instead of resistance, because impedance contains both resistance and reactance. So rotor current be equal to the voltage over the resistance, but in this case we are saying the EMF, which is kind of in volts, EMF over the impedance, which is also in ohms. Okay, so we just move down by saying this EMF, which is same as this, and of course, like I said, that our impedance is a sum, or we can say, using that idea of Pythagoras. Look at this up here. at this up here. So if you use Pythagoras theorem, you have this, you have this, of course you have this, and then once you do this, you have this. So we can actually replace this impedance by everything here, which we just did here, okay. So we'll now save this, say this is for the I2. That means in this formula for starting torque, we can place everything here in this part, I2. Are we saying it? But before we continue, let's consider the power factor. Okay, now for our power factor cos phi, we'll have this y. Now the reason we have this is because this is our resistance and this is our what? Impedance. Okay, so where is this diagram again? Yeah, cos phi. Cos is what? Cos is adjacent over hypotenuse. Okay, so adjacent, this is the adjacent R2 over what? Hypotenuse Z2. So cos phi will be this over this. So we'll come here and look at it. Yeah. Okay, adjacent over what? Hypotenuse. So we have this guy here, and of course we've already defined why Z2 equals this, which is what we have here. Okay, I hope we are following. Now this also can be substituted into this formula right here. Okay, now which is what we did next, saying thus starting torque equals, of course the K remains, then we bring everything here into E2, we bring everything here into cos phi 2. That's what we have here. Okay, already we have one E2 there, so this E2 will give us another E2, and then all over this guy here, this guy here, and this guy here, and then you just simplify to have this. Okay, of course when this multiply this square root sign will cancel out and we'll just have only this guy here, and of course everything here is the same as this, just that this one is squared, this one is squared, meaning our Z2 will be what? Squared. Okay, so that is what we have, that's what we have. Okay, but also this R K, we did not simplify it too. Remember that K equals this. This is kind of something we just have to memorize. However, there's a working for it, but for now just bear in mind that K is 3 over 2 pi ns, which is the speed of which is the synchronous speed. Okay, speed of the stator field. Okay, stator field, the rotating field of the stator. Okay, we've said this in previous video also. Now we can say this K is what we have here. That means this is the K. Okay, dot E2 square R2, which is what we have here, all over this, You can erase everything here and just put Z2 squared. You still be correct. Okay, so yeah, so this is where we'll stop in this video, and in the next one we'll continue and talk about this guy. Okay, so yeah, thanks for watching, and like and subscribe. I'll see you in the next video. Bye for now.